Okay, so today we will start discussing about the transformer, which is generally nowadays a very well known term, and large number of people use transformers in different forms. Okay, firstly, let us know what is a transformer. What is a transformer? What do you know about it, if you know? Now, the transformer is an electromagnetic stationary device It is an electromagnetic device and a stationary device having a common core with multiple windings. And I would say multiple windings, there could be several windings, normally two windings. Okay, this is what we call it as a transformer. Now, yes, it is not moving. Okay, so no part is moving. Okay, so it has no moving part. Okay, what I mean is no moving part in a transformer. Unlike, for example, a motor. Okay? So it is an electromagnetic device having multiple windings wound on common core, and normally two windings are there. Okay. Now, what are the functions of this? What can it do? What can a transformer do?
Increase or decrease the voltage?
So it does voltage transformation. This is one function. It transforms the voltage from one level to another, but these voltages are AC fixed frequency. Okay? AC fixed frequency, and it transforms at the same frequency, no frequency change.
So it can't transform DC voltages?
It cannot transform DC voltages, that's correct. Okay? It is by the principle of induction, change of flux, and change of flux is not prevalent in a stationary flux or a constant flux. Okay? You require, for the principle of a transformer, a time varying flux. That is why it can only operate on AC, and therefore only operates on AC. And it is this great invention of the transformer which made the AC transmission and distribution a universal phenomenon. Okay? This is one of the reasons. Therefore, what we say historically, it is this phenomena which has made the AC to be the general pattern of power generation, transmission, distribution, and utilization. Okay?
So what is the importance of the no frequency change? Can't the frequency change?
In a transformer, frequency is not changed. Whatever frequency you have in one side, the same frequency will be on the other side. Okay? You just cannot change the frequency. If you have put 50 hertz on one side, you can't get 100 hertz on the other side. Transformer will not do that. Okay?
So why that input frequency has to be fixed?
Input frequency is, it operates under a constant frequency mode on a given situation. It need not be fixed. See, it operates for a given frequency. You can change the frequency, but on a given situation, it is that means a frequency, whatever frequency you put in, the same frequency you get it out. Okay. Now, then other thing is, it also does current transformation. It can change level of currents. Just like it can change level of voltages, it can also change the level of currents. Okay? But it transforms power. So power is transferred but you don't expect any change in power. From one side to another, power is transferred through the magnetic media. Okay? So power, volt ampere, all the things are transferred. So transformer also transfers power. Okay? Then what other thing it does? It can also affect impedance transformation. So it transforms, one level of impedance on one side can be changed to some other level of impedance. This is another function of a transformer. And it also does electrical isolation. Because normally in the two windings are normally not electrically connected. They are only coupled magnetically. So these are the functions of a transformer. Okay?
So can it induce a phase change?
Yes, it can. We will see that it can induce a phase change depending upon how you connect them. Either they can be in phase or out of phase by 180 degrees. Okay? And if you want to create, it will be zero. Ideally, the phase change between one voltage on one side to another winding is generally either 0 or 180 degrees. Okay? It can't be, you can't say I will have a 55 degrees. For that you may have a combination of factors. But that's a little complicated issue. Okay? Okay, now we have seen what is a transformer and what are its functions. Now, where are they used? Okay. Where they are used? Number one is power systems. In power systems they are used because this transformer is the one which facilitates the generation of voltage at an optimum frequency, optimum voltage, transmission at an optimum voltage, then the distribution in an optimum voltage and utilization in an optimum voltage. So typically, for example, you can have, for example, you can have a generator. Maybe it may be producing, let us say, a normal large generators may be producing at about say 11 kV. Okay, Then what you do is you step it up, maybe in stages. This is a transformer. And may go to high voltages, say 220 kV or 400 kV or 600 kV, high voltages. So these are called high voltage, or even it is also called extra high voltage, EHV, HV or EHV. And that means from generation level you go to the transmission level. So this is the generation. Okay. Then after long distances transmission, then you come nearer to the load and you come to, you step it down to a distribution to again say 33 kV or 11 kV in stages. Okay, it may come down. So you come to a distribution stage nearer to the load centers like cities, etc. Okay, and then you have come to utilization. This is the load utilization. So where from 11 kV you come down to 415 volts 3 phase or 230 volts single phase, and of course in some countries they are also 110 volts, 110 or 120 volts. Okay. So you will notice that how the transformation has taken place because of this transformer. So that is why this transformer technology has become very important, and you are operating at very, very high voltages. You must have take care of their very high voltage problems. So the whole gamut of high voltage engineering was developed because of these technologies. So, and you will also see these transmission systems can be part of an interconnected grid. Okay. So a national grid is formed from which not only one generator but several generators may be feeding to this transmission network. So you can imagine a whole web of power networks. In fact, nowadays they are also thinking you can use the same lines for communication also, optical communication and optical fibers and so on. So I think there is a very great spur in research and development, and new technologies are likely to come. In fact, recently there was an article on IEEE spectrum where you can different utilities. Of course, it's not happening in India. In Western countries, there is a utilities are investing on power development, and they want to sort of attract the customers to take their power. Okay. In America, there are several telephone companies. They will bid for the customers. Okay, I will give you telephone. Okay. So that way, several companies may say, okay, you take my power. Okay. Right. So it is possible there should be some mechanism which in the same way you don't know whose power is going. Okay. And which there are also very interesting type of technologies which are coming with the combination of present information technology, computers, and then communication systems as well as the power generation. So you are going into a lot of interconnected thing. In fact, they are thinking we can have a same system for both power and communication. Yeah.
Sir, for high voltage DC transmission,
Yeah.
these transformers can't be used.
Yeah, okay. Now we come to, this is AC transmission. So you want okay, if you want a high voltage DC, only thing you do is, just a minute, you generate, then you have a HVDC. For HVDC, all you have is, here is a rectifier unit, which is a controlled rectifier unit. Okay, and you have the DC link here. You step it up, go to DC. Okay, again you need to step up, you require a transformer anyway. And then what you do is, from DC you have to have a AC. So from AC here to it will become DC, and again you go to AC near the load terminals. Okay.
Sir, how do you convert a DC
How do you convert a DC into AC? That's very interesting. You can convert AC into DC. No problem. Okay. What you do is you put a diode, and diode will say, okay, I will open the gate one way and I will not allow the other way. Okay. And now what you do is, can anyone think how you can have a AC from DC? No?
You can have a motor type device which can keep on revolving and giving switches.
Okay, you can have a, that means you are having a, I don't want anything to motor. I would say there is a supply here. Okay. What I will do is, I will have some type of a switch. Maybe, I don't know. Okay. A switch which is connected to the load. Now that switch can be in such a way okay, this is my switch. Okay. What I do is, one time I put it on this side, another I put it on the side. All you need is a human being, DC here. He will go on doing like this. Okay, at 50 cycles per second. If it is feasible, if you want 50 cycles on this side, okay, but you don't have to bother about human being now, because nowadays electronics is helping us. That is, you can have a electronic switch. A transistor can be operated as a switch. A power devices can operate as a switch at very high frequencies. All you do is, you go on triggering them by very high frequency pulses.
So in that case, it won't be a step function like this. It will not be sinusoidal.
Yeah, it will not be. Yes, it will not be sinusoidal. Now only, that's why then the so-called filter technology has come. Okay, it is, filters are there. Not only that, you know, in fact, it can. In fact, nowadays it is again a new technology called pulse width modulation. Say these pulses. See, what you expect here is something like this. If you do this, you expect something like this. Okay, and depending upon RL circuit, it may even become something like this. Okay. Okay. Now, in fact, it is also said that it can even be sort of stepped one. You can have 2 voltage levels, etc. You can make this when you are doing it, step it and make it sinusoidal, or you can also have, you know, you sort of switch on and off in pulses like this. The same thing are switched on and off in pulses, both in positive and negative cycles, so that this becomes more nearly sinusoidal. Okay, this is called pulse width modulation. The width is being changed. So these are all now, it can all be done intelligent control. All you have to do is software programming. Okay, so you program in such a way that that transistor will go on switching at different time interval. It can be programmed. Nowadays, even that is not required. The chips are available, which has been, which are available. You have modules available to you, so which can do. So this so-called power electronics has become a very wide area where you have a combination of power and electronics. Okay, because you know there are basically two type of technologies. One is electronics or communication, and power and electronics. In one communication, the person is not bothered about power. All he is interested in is the quality of the signal, fidelity of the signal. So he is bothered about the voltage only. But it is in the come to power, you are bothered about the voltage into current. Okay? This is the most important things. You are talking about V into I, there which is only V. This is all the difference in the communication system and the power system. Okay? So here you are bothered about the combination, because there no work need to be done. Here work has to be done. Okay? There only people can talk and communicate. Right. Okay. Now you have seen about the use in power systems. Okay. Next is industries. In most of the industries, transformers are used because whatever power that they get in, it must be stepped down to appropriate levels for the process. Okay, so that is, it is used for different processes. So industries is quite widely different transformers are used requirement. For example, if it's welding required, you have welding transformer. You have some heating or induction heating, you may have some different transformers. So we have one in power system and industries. Then you use in communication. In communication systems, they are basically used for audio frequencies, and they are used for example, isolation, impedance matching, and various functions. So you find in communication circuits also different transformers are there. But only thing is they operate at high frequencies, maybe a few kilohertz. Okay, whereas in power system it is 50 hertz operation. Okay. They are all audio frequency for electrical isolation, for impedance matching, and these applications communication. And they are also used in electronic circuits. Again for the similar functions. In electronic circuits, if it is analog or digital, they are used for the purposes of relevant voltage levels, whether DC or AC. Even DC to AC also you will have some power supplies and so on. Then they are used in all the entertainment gadgets. That means, you know, the first point in any of your domestic entertainment gadget, like a TV or whatever it is a transformer. The first point is a transformer when supply goes. Only because that is one which will step down to appropriate AC or DC levels inside an electronic circuit. Okay? So this is quite a common thing to have a transformer available there. Okay, they are also used in digital circuits and computers. See, for example, you are heard of any computer, the power supply is an important component. Okay, and they are also called SMPS, or switched mode power supply, where from AC you go into the inside the computer to appropriate levels to operate different gadgets. You may have there are several gadgets are there. There are some static, there are moving. There are motors inside the floppy drives and so on. There's something or the other moving in a printer. In a printer also there are some movements are there. So you must provide necessary voltage levels in all these information technology equipments. So they are very much used in the in digital circuits and computers. Okay. Then anywhere else they are used?
So CRT, cathode ray tubes.
Yeah, they come part of the electronics circuit. Okay, you said maybe we will call this as instrumentation. Instrumentation, then data acquisition, and also maybe recording. Okay, so they are all the applications where these transformers are required. Instrumentation, especially if you want to have measure very high voltage or very high currents, you have an instrument which will step it down and give it to for a data acquisition system. So that means basically signal conditioning. You condition the signal to be faced with for your recording purposes, because nowadays most of the things you would like to, you will record it on a PC, for example. So there is an interface card. So you must bring it down to an analog signal, then to a digital signal, and get it to the PC. So then processing can be done. So at several stages, these transformers or signal conditioners are being used. So these are several possible application of transformers. Now you see it's wide gamut of applications. So it is apparently impossible for anybody to live without a transformer, it appears. Okay? Because he will be involved with some human activity in any one of them. Okay? Even the person who steals power also may require a transformer. Okay? Power theft also maybe. Okay? But that can't be officially listed here. Okay? Okay. Now with this whole gamut, what is the size of transformer? What is the smallest and the biggest you can think of? Smallest could be around maybe 1 centimeter cube. Okay? I mean, I would say this because you need to connect something also. Screwdriver has to go and things like that. So that is the smallest where you have something. And the biggest could be maybe the one which can be sit on this roof. Okay, a big transformers in large substations and so on, they are as big as this room. Okay, so maybe 10 meter by 10 meter by 10 meter you can say. I'm just approximately giving this size. Okay.
So can a transformer come in an IC chip?
Transformer, no, transformer cannot come in an IC chip. Because there it's all electrostatic. Okay, there's no electromagnetic in an IC chip. Okay? So that's not possible. So we have a overview of this transformer. Okay. Now let us look at how it works. So when we know how it works, you should know what is the basic configuration. Okay. So we have said that broadly there is a core. This is more symbolic. Okay. There is a core on which you said there is a winding. There are several more than one winding. Okay. There is a winding and you apply a voltage to one winding, let us say V1, at a fixed frequency, and it will draw a current I1. Okay. Then we said this should be more than one winding. So let us put another winding. And normally across other winding, you connect a load. So you connect a load to the other winding, and generally there is a voltage. I mean, of course, when you close the switch, the voltage here, let us say, is across the load is V2, and the current that is drawn, let us say, is I2 when it is loaded. This is a general thing. Okay. This is a common. This is one of the basic thing of a transformer. Now, this and linking these two is a common flux. in the core. This is the core. Okay. Now, the winding to which you are connecting a supply is called primary winding. So it's called a primary winding where you connect to a supply. That is the definition. So you say primary winding that is connected to supply, and the one connected to the load is called what? Secondary winding. So the one connected to the load is called a secondary winding. So we write the secondary winding that is connected to load. Okay? And the primary winding may have a turns N1 and secondary winding may have a turns N2. Okay? And V2 and V1 are not necessarily the same. Okay? Now, if V2 is more than V1, we call this transformer as a step-up transformer. So, if the secondary voltage more than the primary voltage, it is called a step-up transformer, and other way, if V1 is more than V2, it is step-down transformer. These are very simple things. Okay? These are our definition. Either we step up a transformer or step down a transformer, and you will see there is no electrical connection between the primary and the secondary. Okay. Now, the next question is, how do you connect wind it, the secondary one? Okay. Is this a correct way, or I should go the other way around? Huh? Think about it. Is it a correct way if I have put it like this? Okay. Okay. Now, a basic function of transformer, you will notice there is a flux, let us say phi. Okay, there is a flux phi, and because of flux phi, so phi you can say is phi max, let us say sin omega t, the flux, which is the one which is linking both the primary and secondary, and it induces a voltage E1 in primary and also induces a voltage E2 in secondary. The flux, so what is the voltage E1 that will be induced will be N1 d phi by dt. Okay, and E2 will be N2 d phi by dt for the direction which we have already shown. In fact, earlier we have clarified this, why we call, if it is E1 it is plus N1 d phi by dt, if it is other way around minus N1 d phi by dt. Okay. Now, this is instantaneously, you will have that E1 will be N1 omega phi max cos omega t, and E2 would be N2 omega phi max cos omega t. Okay, yes. E2 should not be? No, I have taken, this is the E2. Now, if you are having like this, okay, then when flux is going, this is E1, and the flux is going, it is like this. Yeah. Pardon, just a minute. Huh?
E2 direction you've taken that is opposite to the flux.
No, I have taken E2 direction similar to this, because E2 will be induced in such a way to oppose the flux. Okay, so this one going in, see the thing is, we should say when the current is going in, whether it is in primary and secondary, the flux direction must be same. So when the current is going in like this, then the flux is here. When the current is going in like this, the flux is down. It is the same direction of flux. No, just a minute. We are not, no, as far as the current, that is what I am saying. If this is wound like this, now the current is going in, I put a dot here. Now I will also say current is going in. So if in the current is going in, the flux direction is the same way, they are coupled together. So we represent this one as a, when the current is going in, I mean, don't bother, we are not, assume that we are not loaded it. That is a different issue. That current goes out is because of the load. If you apply, okay. Now, that's why I expected you to have doubts at this point in time. Because this doubt will perpetually have unless you clarify at this point in time. Now, we show that this is how we indicate a mutual inductance. Have you heard about this? We show these dots. What does it mean? That means it's wound in such a way that when the current is going in, it will produce the flux in the same direction as this one.
So the flux is the net due to I1 as well as I2?
Yeah, if there is I2. If there is no I2, it is the flux due to this one. Okay? You are adding another element of I. Let's not bother about it now. Okay?
So if you assume it is not loaded,
Uh-huh.
the secondary is not loaded.
Yeah. But still there is an E2 is there. Okay, and we have already several times I have clarified that Lenz's law will act in such a direction as to pump out a current to oppose the flux. Okay, this was clarified. Okay, when we went to Lenz's law. Okay, now if this is the direction of E2, we have seen that E1 and E2 will be this. On that there is no doubt. Okay, if we have no doubt at this point of time. Okay, now. What we mean is E1 and E2, see if this is E1 and this is E2, I mean I am just writing a sinusoidal, doesn't matter, they are in phase. Okay, so this is proportional to N1, this is proportional to N2. Okay, they are in phase. According to this I say, and with peak value is N1 omega phi max and this is N2 omega phi max. Okay? And what is the RMS value? And we have E1 RMS will be omega N1 phi max by root 2. Okay, this is nothing but 4.44 F N1 phi max, and E2 is 4.44 F N2 phi max. Because the same flux is linking both. We are neglecting all leakage fluxes and everything. Same flux is linking both. You at this point at time just blank out everything else and assume there is a common flux linking both the windings. Okay, and two windings are faithful neighbors. Okay, and no quarrels among them, and one gets E1 induced, another gets E2 induced.
Which are in phase.
Yeah, which are in phase.
But so they can't be in phase.
What is all this? I say, you have whole story I have told, and finally you again say they are in phase.
So please explain again that.
E1, E2 you have seen. E1 is N1 d5 by dt, E2 is N2 d5 by dt. So, okay, up to that point it's clear. We get this expression E1, E2. You find E1, E2 are time phased same way. Both is cos omega, both are cos omega t. Okay, so if this is E1 and this is E2, because you know the flux here is going up and flux here is going down here, so that's why E2 has to be like this. Okay, right? Therefore, in this case, you will have, if this is E1 phasor, this will be E2 phasor. They will be in phase. There is no other way. Acha, now if you want to make it out of phase, is it possible or not? How? All you do is to go, you know, rewind the other way around. So in that case, okay, in that case, this is one possibility, and it is possible to wind the other way around. Nobody is preventing you from winding the other way around. Okay, so you can wind it the other way around. So that the current doesn't go from the top; it goes from the other side of the core. Okay, you go from the other side of the core and do like this. Then what will happen? Whenever the current enters, the flux is going up. Whenever the current enters, the flux is going up. Whereas whenever current goes, flux is going up. That means the flux here will be opposite to the flux here. So if you want the flux to go in the same direction, you must pump in current from the bottom. Is it clear? You must put the current from the bottom if you want to produce the same flux if it is wound the other way around. So in that case, we symbolically write like this. Okay, here in this case, this is E1 and this is E2. Okay, and if you show E1 here and E2 here, okay, in this case what will it be? Where will E2 be? So there will be E1 and this will be E2. Okay, have you got this clear? I knew that you will have doubts. Okay. Okay, then what I suggest is, the only remedy is, worth of the pudding is in the eating. Go to the laboratory, look at the, measure the E1 and E2 with the two windings separately. Okay, and look at its waveforms. Okay, if you wind the other way around, I hope you understand, if you wind the other way around, voltage will be out of phase by 180 degrees. So in this case, so for the directions how it is wound, see, for the second case you will have E1 like this and you will have E2 like this. Okay, if it is wound the other way, right? If you wind the other way, this will be the direction. Of course, if you indicate E2 to be like this, or E2 dash, I would say. Supposing I have E2 dash, right? You please, no, I think, listen very carefully. If I put E2 dash is like this, then my E2 dash will be, okay? Is it clear now? So it is either you can have a 0 degrees phase shift or a 180 degree phase shift, an ideal transformer, because the two windings are on the same pattern.
So we are neglecting self-inductance.
What? We are not neglecting anything as such. Inductance is there. It is due to inductance only all this is happening.
Self-inductance.
Leakage you have neglected, yes, not self. Because the whole flux is linking both. What is inductance is the flux linkage per unit current. Okay? Okay? Now, I think this direction clarification, now you should not have doubts. Okay? Now, what is E1 by E2? Let us look at the voltage ratio. Voltage ratio E1 by E2 is? It is simple. So this is known. This is a well-known transformer formula. E1 by E2 is equal to N1 by N2. Very simple. Okay. Now, so much so good. Okay. Now, in an ideal transformer, okay, let us take an ideal transformer. Ideal transformer, I mean all the flux is faithful linking only the core, okay, all flux in core, no leakage flux, no fringing, okay. I mean, I would say no copper loss, that means your windings are supposed to have a almost negligible resistance, okay, ideal transformer. Then no core loss, no hysteresis, no eddy currents, okay. So you have, this is ideal, and core is infinitely permeable, has mu equal to infinity. Core is infinitely permeable. What do you mean by core is infinitely permeable? It doesn't require any current for the flux, okay. That means, it means 0 Im to cause flux. Infinitely permeable means it doesn't draw anything. Yeah?
So
Okay.
the point is that there is no current for flux. Without how can you have flux without the current?
Yeah, because this is infinitely permeable. Mu is infinity ideally. Pardon? Yeah, but that current is negligible. Yeah. Okay. Now, I mean, after all, it is never infinity, isn't it? Okay. Now that means you require a 0 net MMF in the core. You will have a net MMF is 0 in the core, which would mean that N1 I1 plus N2 I2 is always negligible, 0, isn't it? After all, there will be something that will come to that later if it is not, but as an ideal condition we have said this. Now, this is what will happen. Now let us look at a little more detail. What does it mean? Whenever you load the transformer secondary, that means whenever I2 was 0, what would be I1? I1 would be 0, because ideally nothing for supplying core loss, nothing for magnetizing, okay. So when I2 is 0, I1 is 0. This is the first thing. When I2 is 0, that is no load, I1 is 0. No current from the primary at all on no load, okay. But when you load the secondary, when secondary is loaded, okay, then what will happen? Then it will start adding an MMF, okay. When you start adding an MMF, that means the flux will start changing. Then in order to maintain the constancy of flux, then it will start drawing a current. So this is a phenomenon that takes place. As soon as you start drawing a current here, this winding will also start drawing a current from the mains to compensate for that MMF. Okay? So that is on load. That means on load, when I2 is not 0, the I1 is drawn to compensate for the MMF. Okay? and it which such that N1 I1 plus N2 I2 is 0. Which one? That is the total MMF on the core. Say I am plotting. So the current, whenever this is carrying a current I1 and this is carrying a current I2, okay, the total MMF will be this MMF plus this MMF, isn't it? N1 I1, because if you take an H dot dl, you know, will be current enclosed is this current enclosed together. N1 I1 plus N2 I2 is the total MMF acting on the core, okay, which will produce the flux. Now that is supposed to be negligible or 0. Yeah, that's exactly. So we are in this is formula when I2 is going in, right? Here I2 is going in, because that only then this MMF. If I2 is going out, minus. So if I2 is going out of the from going out from the top of the winding, that is from this point, if this is the I2 which is going out, so then the net MMF will be N1 I1 minus N2 I2 is 0. So you will find that I1 by I2 will become N2 by N1. So we get another relation of a current transformation, right? You will have I1 by I2 is equal to N2 by N1, and that means if you step up the voltage, you will step down the current, okay? And what will be V1 I1? So therefore V1 I1 is equal to V2 I2, okay? So we come to these 3 points now before we close: voltage transformation, current transformation, and volt ampere transformation. If voltage goes up, current goes down, and volt ampere remains the same, okay? So this is the basics of transformer. We'll take it in next class, okay?